What if I told you that somewhere in this vast universe there are planets where glass falls from the sky, where not one but two suns sink below the horizon, where diamonds may be buried like ordinary stone beneath the surface, and where some worlds drift alone, without a star, wandering through endless darkness? Tonight, we will leave our solar system behind. We will travel beyond Mars, beyond Jupiter and Saturn. We will descend into a depth where light becomes only a distant memory. Out there are not thousands, but billions of worlds. Some burn like fire, some rest as quiet as ice, and some move so quickly that their year lasts only a single day. Gently close your eyes. Let your breathing slow. Tonight, we are not just exploring facts, we are listening to the stories of planets. Because the universe does not shout, it slowly reveals its secrets, and we are simply here to listen. Tonight, as we continue drifting beyond the familiar warmth of our sun, imagine the darkness growing softer rather than colder. The stars no longer feel distant and sharp, but gentle and scattered, like quiet lanterns suspended in an endless sea. We have left the edges of our solar system behind, passing the fading glow of Neptune and crossing into the wide interstellar night. Out here, planets do not resemble the orderly worlds we grew up memorizing. They follow different rules, shaped by different stars, born from stranger clouds of gas and dust. Some of the first worlds we encounter are giants that circle impossibly close to their suns. These massive planets rush through their orbits in only a handful of hours, pulled tightly by gravity. Their stars loom enormous in their skies, filling half the horizon with blazing light. One side of these planets faces that brilliance forever, locked in place, absorbing relentless heat. The other side remains in unending darkness. Between them lies a narrow band of twilight, a thin ring where day and night meet in quiet balance. On the scorching day side, temperatures rise so high that rock itself can melt. Entire landscapes may exist as oceans of molten stone, glowing faintly beneath turbulent skies. Winds roar from the hot side to the cold, racing faster than any storm on Earth, redistributing heat in a restless atmospheric dance. Clouds form not from water, but from vaporized minerals, iron, silicates, and exotic compounds lifted upward by intense radiation. These clouds swirl and scatter light in strange hues, deep blues, smoky grays, and faint metallic shimmers. And yet, even in such extremes, there is a quiet rhythm. The planet continues its tight orbit, completing a full year in less time than a single Earth day. Imagine watching the sun rise and set within hours, the sky cycling through brightness and shadow again and again. Time itself would feel compressed, hurried, almost breathless. But not all close-in worlds are giants. Some are rocky, only slightly larger than Earth, skimming so near to their stars that gravity stretches them subtly, pulling at their crusts with invisible tension. These planets may glow dimly red from heat alone, their surfaces cracked and reshaped by constant tidal forces. They exist on the very edge of survival, balanced between cohesion and collapse. As we drift past these hurried worlds, it becomes clear that planets are not static objects. They are living systems of motion and energy, shaped continuously by their stars. Some are slowly losing their atmospheres, heated until their outer layers escape into space, trailing behind like faint luminous veils. Others may endure for billions of years, locked in this intense embrace. And still, Beyond these blazing realms, the darkness stretches onward. There are calmer places ahead, worlds less hurried, less fierce. As we continue deeper into the galaxy, the heat softens, the orbits widen, and the universe begins to reveal gentler possibilities waiting quietly in the distance. As we move farther from those hurried, star-skimming worlds, the heat begins to fade. The fierce glow softens into something steadier, and orbits widen into long, patient paths. Out here, planets are not racing against their suns. They travel slowly, sometimes taking decades, sometimes centuries to complete a single journey. Time feels stretched and generous. A year is not a brief flash of motion, but a quiet arc traced across generations. Some of these distant planets are ocean worlds. Imagine a globe almost entirely covered in water. No continents rising above the waves, no mountains breaking the horizon. Just a single endless sea wrapping the planet in reflective calm. From space, such a world might shimmer deep blue, clouds drifting lazily across its surface. But beneath that surface lies depth beyond anything on Earth. On our planet, the deepest ocean trenches descend only a few miles. On these distant worlds, the water layer could plunge hundreds of miles down. As you drift deeper in your mind, the pressure grows immense. Water changes under such crushing force. It transforms into exotic forms of ice, not the brittle ice we know, but dense, crystalline structures formed purely by pressure rather than cold. Far below the rolling surface, a thick mantle of high-pressure ice may separate the upper ocean from a rocky core hidden in darkness. Yet warmth can still exist there. Some ocean worlds may generate internal heat from radioactive elements within their cores. That heat could keep portions of the deep ocean liquid, even far from their star's light. Gentle convection currents might circulate nutrients through those hidden waters. In the quiet blackness beneath miles of sea, chemistry could unfold slowly, patiently. Whether life could arise there remains unknown, but the possibility lingers like a soft echo. Other planets in these distant orbits are not made of water at all. Some are rich in carbon, born around stars where carbon outnumbers oxygen. Under extraordinary pressure, carbon atoms can compress into crystalline forms. Deep beneath their surfaces, vast layers of diamond may exist, not sparkling in sunlight, but locked in darkness, silent and immense. Mountains on such a world might be dark and glassy, their true brilliance hidden below. The sky above these calmer planets would feel different from the frantic blaze we passed earlier. Their stars appear smaller, gentler, rising and setting slowly across long seasons. Winds may move in measured patterns rather than violent surges. Clouds gather, drift, and dissolve in cycles that unfold over years. And as we continue outward, leaving behind both scorching giants and endless seas, the galaxy grows quieter still. Ahead lie stranger configurations, systems where not one sun lights the sky, but two, moving together in an intricate gravitational dance, shaping worlds in ways both delicate and surprising. Ahead of us, the darkness does not empty. It rearranges itself. Two stars appear where one might be expected, circling each other in a slow and graceful dance. Around them, held carefully in balance, is a planet tracing a wide, looping path. These are circumbinary worlds, planets that do not belong to a single sun, but to a pair. From the surface of such a world, the sky would never look entirely familiar. At times, both stars might hang together, close and brilliant, casting layered shadows that stretch in different directions. At other times, one star would lead while the other trails behind, rising and setting in a rhythm more complex than any single sunrise. Some days would glow brighter than others. Some nights might never grow fully dark. The gravity in these systems is delicate but steady. For a planet to survive here, its orbit must be carefully placed, far enough from the twin stars to avoid chaotic pulls, yet close enough to remain bound. Once settled into that balance, the motion becomes almost musical. The stars revolve around each other while the planet circles them both, a choreography that can last billions of years. Seasons on such a world would feel unusual. The combined warmth of two suns could shift subtly as the stars move closer together or drift slightly apart in their shared orbit. Light might vary not only by the planet's tilt, but by the changing geometry of the twin stars themselves. Imagine standing on a quiet shoreline, watching one sunset fade while another lingers higher in the sky, casting a second softer glow across the water. Not all multi-star systems hold planets in wide orbits like this. Some planets circle just one star, while a distant companion star shines far away, tugging gently over long stretches of time. Its gravitational influence may tilt the planet's orbit or stretch it into a slow ellipse. Even subtle shifts can reshape climates over millions of years. Despite the complexity, planets continue to form in these systems. Disks of gas and dust swirl around young binary stars, much as they do around single stars. Within those disks, particles collide, clump together, and gradually build worlds. Gravity finds stability more often than we once believed possible. And as we drift past these twin-lit skies, another pattern begins to reveal itself. Not every planet belongs to a star at all. Beyond the reach of even paired suns, there are darker paths, lonely trajectories where a world moves without sunrise, without sunset, guided only by its own momentum through the vast and silent black. As we drift beyond the reach of twin suns, the light thins again, until even distant stars feel like scattered embers. And here, in this quieter expanse, we encounter something even stranger: planets that belong to no star at all. These are the Wanderers, rogue worlds moving freely through the galaxy, untethered, unlit by any sunrise. They may once have formed in ordinary systems, circling a star in calm repetition, before a gravitational disturbance altered their fate. A passing giant planet, a close stellar encounter, or the slow instability of orbital motion could have cast them outward, releasing them into interstellar space. Once free, they would never return. Without a star, their skies would hold no bright disk of light. No dawn would spread across their horizons. Instead, the stars would remain fixed points in an endless night, sharp and constant. The surface of such a planet would grow cold over time, its atmosphere freezing or collapsing inward. Oceans, if they once existed, might solidify into thick shells of ice. And yet, even here, warmth can linger. Deep within a planet's core, radioactive elements slowly decay, releasing heat over billions of years. That internal warmth does not depend on starlight. Beneath a frozen crust, insulated by layers of ice, liquid water could remain hidden in subsurface oceans. In the silent dark below, chemistry might continue, slow, patient, shielded from the vacuum above. Some rogue planets are enormous, gas giants that glow faintly in infrared, still radiating leftover heat from their formation. They drift like dim lanterns through the galaxy, detectable only by their subtle warmth against the cosmic background. Others may be smaller, rocky, and almost invisible, discovered only when their gravity briefly bends the light of a more distant star in a phenomenon called gravitational microlensing. For a moment, the background star brightens, revealing the unseen mass that passed between. Imagine standing on such a world. There would be no sunrise to mark time, no sunset to close the day. Only the steady, unchanging canopy of stars. The Milky Way would stretch brilliant and wide across the sky, unspoiled by glare. Time might feel slower there, measured not by light, but by subtle internal shifts, cooling crusts, drifting ice, quiet tectonic murmurs beneath your feet. These lonely planets remind us that belonging to a star is not required for existence. Gravity shapes them, physics sustains them. They travel silently through the galaxy, carrying whatever stories began at their birth. And as we continue drifting outward, another kind of world begins to shimmer ahead. Planets so dark they seem to swallow light itself, nearly invisible even while orbiting bright and blazing suns. Beyond the silent wanderers, we return once more to the presence of stars, but these are not gentle systems. Here light shines brightly, yet something about it feels muted. As we draw closer, we notice the reason. There are planets orbiting these suns that reflect almost nothing at all. Some worlds are darker than charcoal. They absorb nearly every ray of starlight that touches them. Instead of gleaming or shimmering, they appear as faint silhouettes against the glow of their stars. Their atmospheres may contain vaporized metals or unusual chemical compounds that trap incoming light, preventing it from scattering back into space. Where we might expect a bright gas giant, we find instead a sphere as black as ink. If you could approach one of these planets, you would not see a colorful banded surface like Jupiter's. You might only see a dim outline, a shadow moving quietly across the star's brilliance. Even the day side would not shine brightly. It would glow faintly from heat rather than reflected light, radiating in subtle infrared tones invisible to human eyes. Temperatures on such worlds can still be extreme. Some orbit close to their suns, completing a full year in only a few days. Intense radiation heats their upper atmospheres, stirring fierce winds that circle the planet at extraordinary speeds. But despite the violence of their weather, they remain visually subdued, absorbing energy rather than returning it. On the night side, darkness deepens even further. With so little reflected light, the transition from day to night might feel less dramatic than on Earth. There would be no soft twilight glow, only a steady dimming into shadow. And yet the planet would continue its orbit faithfully, bound by gravity, invisible except for the subtle tug it exerts on its star. Astronomers detect these worlds not by sight, but by motion and shadow. When they pass in front of their star, the starlight dips slightly. When they pull gently on the star, its light shifts in measurable ways. Even the darkest planet leaves a trace, a quiet signature written into starlight. These shadowed worlds remind us that brightness is not the only form of presence. Some planets exist in near invisibility, absorbing the light of their suns and giving little back. They circle in silence, their surfaces hidden, their storms unseen. And as we drift beyond them, the galaxy reveals yet another possibility. Worlds where the skies themselves may shimmer not with water clouds, but with minerals, metals, and even crystals suspended high above alien landscapes. As we leave behind those nearly invisible worlds, something unexpected begins to glow ahead of us. Not brightness in the usual sense, but color. Subtle hues ripple through distant atmospheres, hints of crimson, violet, and deep metallic blue. These are planets where the clouds themselves are not made of water vapor, but of minerals and metals lifted high into alien skies. On some intensely hot gas giants, temperatures rise above 2,000 degrees. At such extremes, substances we consider solid on Earth, iron, aluminum compounds, silicates, can vaporize into gas. Carried upward by turbulent winds, these materials cool slightly in the upper atmosphere and condense into tiny droplets or crystalline particles. In place of soft white clouds, these planets may host drifting layers of iron mist, silicate haze, or even corundum, the mineral form of rubies and sapphires. Imagine looking upward from the surface of such a world. The sky might glow faintly red or shimmer with a smoky purple cast. Light from the nearby star would scatter through mineral particles, creating strange halos and shifting tones. Storm systems could carry metallic clouds across the horizon, flashing faintly as lightning flickers within them. Instead of rainwater, droplets and molten material might fall, only to evaporate again in the intense heat below. Some of these planets are tidally locked, keeping one hemisphere always turned toward their star. On the scorching day side, mineral vapors rise continuously. Winds then sweep them toward the cooler night side, where they condense and settle. In this way, entire atmospheric cycles unfold, not of water, but of rock and metal, circulating endlessly between heat and shadow. Even on slightly cooler worlds, exotic cloud chemistry can take shape. Methane, ammonia, or sulfur compounds may gather into thick layers, forming hazes that obscure the surface completely. From a distance, such planets appear smooth and uniform, wrapped in soft color. But beneath those clouds, winds roar and temperatures shift in complex patterns. Astronomers have learned to detect these distant clouds by studying how starlight filters through a planet's atmosphere during transit. Certain wavelengths are absorbed, others scattered. Each element leaves a delicate fingerprint in the spectrum of light. From those subtle signals, we infer the presence of clouds composed not of water, but of unfamiliar substances. These mineral skies remind us that weather is not unique to Earth's gentle cycles. Across the galaxy, atmospheres churn in ways both violent and beautiful. Clouds drift, storms gather, and rain falls, sometimes in forms we would never recognize. And as we continue outward, the pace of motion begins to shift again. Some worlds race through tight orbits, but others move with extraordinary slowness, tracing arcs so vast that a single year may last longer than human history itself. As we move beyond the shimmering mineral skies, the rhythm of motion changes once more. The hurried worlds close to their stars fall behind us, and now we enter regions where orbits stretch wide and slow. Here, a single year is not measured in days or even decades, but in centuries. Planets trace enormous paths around faint, distant suns, completing only a small fraction of their journey within a human lifetime. Imagine a gas giant circling its star so far away that the star appears as nothing more than a bright point in a dim sky. Its orbit may take hundreds, even thousands of Earth years to complete. Seasons on such a world would last generations. If it possessed moons, those moons might experience gradual shifts in light so slow the change would feel almost imperceptible. Entire civilizations could rise and fall without ever witnessing a full seasonal cycle. These long-period planets are difficult to detect. We cannot simply wait centuries to watch them complete an orbit. Instead, astronomers observe tiny segments of their motion, subtle arcs against the backdrop of space, and use careful mathematics to predict the full path. Sometimes we detect them directly through powerful telescopes, capturing faint images of their glow against the darkness. Other times, we infer their presence from the gravitational influence they exert on their star or neighboring planets. Far from their suns, temperatures can drop dramatically. Atmospheres may thicken and cool, forming layers of cloud that drift slowly in subdued light. If oceans exist, they might freeze at the surface while remaining liquid beneath, insulated by thick ice. Internal heat, as on rogue planets, could still play a role, maintaining pockets of warmth far below the crust. In these distant systems, the sky would feel vast and quiet. The parent star would rise slowly, moving across the heavens over many months. Night would reveal a brilliant tapestry of distant stars, undimmed by glare. Comets and icy bodies might wander through elongated orbits, occasionally passing close enough to create brief flares of reflected light. Such worlds remind us that not all planetary systems are compact and tightly wound. Some are expansive and patient, their gravitational ties stretched across immense distances. The pull between star and planet remains steady but gentle, holding them together across cold emptiness. And as we continue drifting beyond these slow travelers, we approach systems where gravity grows even more complex, where not one or two, but three or more stars share the same celestial space, and yet planets still manage to find stable paths within the intricate dance. As we drift onward from those slow and patient worlds, the darkness begins to glow again, not with one sun, nor even two, but with several. Here, gravity weaves a more intricate pattern. Three stars move together in a complex gravitational dance, each tugging on the others in careful balance. And somehow, within that layered motion, planets still form. In these multi-star systems, the sky would never feel entirely still. One star might blaze brightly overhead, while two smaller companions shimmer at a distance, circling one another in a tighter embrace. Their light would overlap and shift, casting multiple shadows that stretch and cross in quiet patterns across the ground. Daylight might vary subtly as the positions of the stars change, creating rhythms more intricate than any single sunrise and sunset. For a planet to survive here, its orbit must be placed with remarkable precision. Too close to one star, and the gravitational pull of another could destabilize it. Too far, and it might drift free entirely. But when conditions align, stability emerges from complexity. The planet settles into a steady path, perhaps orbiting one central pair while a third star circles at a greater distance, or tracing a wide orbit around the entire trio as a single gravitational unit. Seasons in such systems would unfold in unusual ways. The combined light of multiple suns could warm the planet unevenly as their relative positions shift. A distant companion star might brighten the sky every few years, adding a faint secondary glow even during what would otherwise be night. Shadows would never be simple. They would layer and merge, soft at the edges where light from different stars overlaps. Despite the apparent chaos, physics maintains quiet order. The same laws that guide our own planet apply here. Dust clouds swirl around newborn multi-star systems, clumping into rocks, then into larger bodies. Over millions of years, planets take shape, finding equilibrium within the gravitational currents. From the surface of such a world, the sky would feel alive with motion. Stars would move against one another in graceful arcs. Eclipses might occur more frequently as one star passes before another. The heavens would not follow a simple daily rhythm, but a shifting choreography unfolding over years. These systems remind us that nature is not limited to simple arrangements. Even in places where gravity pulls in many directions at once, planets can endure. And as we continue our journey, another transformation awaits. Worlds that circle not living stars, but the quiet, collapsed remnants of stars long past their prime, glowing faintly in the aftermath of cosmic endings.
Beyond the bright complexity of multiple suns, the light begins to change again. It grows softer, colder, sometimes flickering faintly, sometimes pulsing with steady precision. Here we encounter planets that orbit not vibrant, burning stars, but the quiet remnants left behind after a star has lived out its life. When stars like our Sun exhaust their fuel, they shed their outer layers and collapse inward, becoming white dwarfs, small, dense stellar cores that glow gently with leftover heat. Larger stars may end more violently, collapsing into neutron stars, or, in the most extreme cases, black holes. And astonishingly, around some of these stellar remnants, planets still exist. Imagine a world circling a white dwarf. The star would appear small in the sky, bright but no longer blinding. Its light would be pale and steady, casting long, cool shadows across the surface. If the planet survived the chaotic transformation of its parent star, the expansion into a red giant and shedding of outer layers, it would now orbit in a very different environment. Temperatures would have shifted dramatically. The star's warmth would slowly fade over billions of years. Some planets may not be survivors at all, but reborn. After a star's explosive death, debris spreads outward, gas, dust, fragments of former worlds. From this scattered material, new disks can form, and within them, new planets may coalesce. These would be second-generation worlds, assembled from the remnants of what once was. Around neutron stars, the situation becomes even stranger. Neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses. If a planet orbits such an object, it would experience intense radiation unless shielded by distance or a thick atmosphere. The sky might flicker rhythmically as the star pulses, marking time with extraordinary precision. And even black holes can host planetary systems. If a black hole formed within a binary system, its gravitational pull could continue binding surrounding material. Planets might orbit at safe distances, tracing silent paths around an invisible center. From their perspective, the black hole would not appear as a dark sphere, but as a distortion, bending the light of background stars into subtle arcs. These worlds orbit in what could be called stellar graveyards, yet they are not places of emptiness. They are reminders that endings in the cosmos often give way to new arrangements. Planets endure, gravity persists, motion continues. And as we drift farther still, we begin to notice something else. Subtle dimmings of distant starlight, tiny flickers that reveal the presence of unseen worlds crossing silently between us and their distant suns.
As we continue outward, the stars ahead appear steady and constant. But if we watch closely, some of them seem to blink. Not dramatically, not like a flickering flame, but with the faintest dip in brightness, a soft dimming, a brief shadow passing across their light. And within that tiny shift, entire worlds are revealed. When a planet moves directly between its star and our distant vantage point, it blocks a small fraction of the starlight. This event is called a transit. The reduction in brightness is often less than 1%, so slight that it requires sensitive instruments to measure. Yet from that subtle dimming, astronomers can learn astonishing details. The depth of the dip tells us the planet's size. A larger planet blocks more light, a smaller one less. The time between repeated dips reveals how long the planet takes to orbit its star. From this, we determine the length of its year and its distance from the star. Even the shape of the light curve, the way the brightness fades and returns, provides clues about the planet's atmosphere. If the planet has an atmosphere, a small portion of starlight filters through it during transit. Certain wavelengths are absorbed by gases such as hydrogen, sodium, or water vapor. These absorbed wavelengths leave faint signatures in the starlight spectrum. By analyzing these patterns, scientists can infer the chemical composition of air on a world light years away. It is remarkable to consider that we do not see most exoplanets directly. We detect them through shadows, through tiny interruptions in starlight. A distant sun shines steadily across space, and for a brief moment, a planet crosses in front of it. That small crossing tells us of an entire world, orbiting in quiet repetition. Thousands of planets have been discovered this way. Some are massive gas giants hugging close to their stars. Others are rocky worlds similar in size to Earth. Each transit is like a whisper from across the galaxy, a subtle message carried in light. If you could stand on one of those transiting planets and look outward, you would see your own star looming bright above you. You would not sense the distant observers measuring your shadow. The motion would feel natural, ordinary, just another orbit in a vast cosmic dance. And as we drift further, another method of discovery begins to reveal itself, not through shadow, but through motion itself, as stars gently sway under the invisible pull of planets too distant to see directly. Beyond the faint flickers of transits, there is another way planets quietly announce themselves, not through shadow, but through motion. Even the largest star does not remain perfectly still. When a planet orbits a star, gravity binds them both. And though the planet travels in a wide circle, the star moves as well, tracing a smaller countermotion around a shared center of mass. This motion is subtle. From a great distance, a star may appear steady and unmoving, But with careful instruments, astronomers detect tiny shifts in its light. As the star moves slightly toward us, its light becomes compressed, shifting toward bluer wavelengths. As it drifts away, the light stretches toward red. This gentle back and forth shift is called the radial velocity effect. Imagine watching a distant lantern sway almost imperceptibly in the dark. You cannot see what is pulling it, but you know something must be there. That unseen presence is the planet, tugging on its star with quiet persistence. The more massive the planet, the stronger the tug. The closer it orbits, the quicker the star's motion repeats. Through these measured wobbles, astronomers have uncovered some of the first exoplanets ever discovered. Many were large gas giants orbiting close to their stars, so-called hot Jupiters, because their gravitational influence was easiest to detect. But over time, as instruments improved, smaller planets revealed themselves through even finer shifts in starlight. The star and planet move together like dance partners connected by gravity. Neither stands still, both respond to the invisible pull between them. Even across light years of space, that relationship leaves a detectable trace. From the size of the wobble, scientists estimate the planet's mass. Combined with transit data, they can determine density, revealing whether a world is rocky like Earth or gaseous like Jupiter. Through light alone, we begin to understand the nature of unseen planets. And still, we rarely observe these worlds directly. They remain points of data, patterns in spectra, rhythms in light. Yet behind each measured curve lies a real place, a sky, a surface, perhaps clouds drifting in unfamiliar colors. As we continue drifting through this widening gallery of worlds, another transformation appears ahead. Some planets orbit so close to their stars that the intense radiation begins to strip their atmospheres away, stretching them into luminous tails that trail behind like comets in slow motion. As we drift closer to certain stars once again, the calm balance of gravity gives way to something more fragile. Here, planets orbit so near to their suns that the boundary between world and space begins to blur. The star's radiation is intense, relentless, pouring outward in waves of ultraviolet light and charged particles. Under such pressure, a planet's atmosphere can begin to escape. Imagine a giant gas planet circling its star in just a few days. Its upper atmosphere absorbs enormous energy, heating and expanding until the outermost layers drift beyond the planet's gravitational hold. Hydrogen and helium, the lightest elements, are the first to slip away. Slowly, steadily, they stream into space, forming a faint tail that trails behind the planet like a ghostly comet. From a distance, astronomers detect this escape through ultraviolet observations. The planet appears larger in certain wavelengths, surrounded by a halo of escaping gas. Over millions or billions of years, this gradual loss can significantly reshape the planet. A once massive gas giant might shrink, stripped down layer by layer. In extreme cases, only a dense rocky core may remain, the quiet remnant of what was once a bloated world. Even smaller rocky planets can lose their atmospheres if they orbit too close to their stars. Without sufficient gravity to hold on to heated gases, they may become barren and airless. Their surfaces, exposed to intense radiation, could melt or crack under tidal stress. The star does not simply illuminate these worlds, it sculpts them. Yet this process is not always destructive. In some systems, atmospheric escape may stabilize over time. A planet might lose only its lightest gases, retaining heavier molecules that form a thinner but enduring atmosphere. Change in the cosmos is rarely sudden. It unfolds gradually through steady interactions between star and planet. If you stood on such a world, assuming it were possible, you might see a glowing stream arching away into space, a constant reminder of the star's influence. The sky would blaze with proximity. Days would pass quickly as the planet rushed through its tight orbit. Seasons would not gently shift, they would scarcely exist at all. These evaporating worlds reveal that planets are not fixed in form. They evolve, they respond, they transform under the forces surrounding them. And as we continue outward once more, leaving behind these shrinking giants, the pace changes again. Ahead lie worlds that move not swiftly, but with astonishing speed, racing around their stars in mere hours, completing a year in less time than a single Earth day.
Beyond the worlds, slowly shedding their atmospheres, we arrive at planets defined not by loss, but by speed. These are the ultra-short period worlds, racing around their stars in astonishingly tight orbits. A full year on such a planet may last only a handful of hours. While Earth takes 365 days to circle the Sun, these planets complete their journey before a single day on Earth has fully passed. Imagine standing on a rocky world so close to its star that the horizon glows constantly. The star would appear enormous in the sky, dominating nearly everything you see. Because of tidal forces, many of these planets are locked in place, always showing the same face to their star. One hemisphere bakes under unending daylight, the other remains trapped in perpetual night. The dayside surface may be an ocean of molten rock, glowing faintly red beneath a thin, heated atmosphere. Lava flows slowly across cracked plains, shimmering in the intense light. Temperatures climb high enough to melt metals and soften stone. On the night side, however, the landscape cools dramatically, forming dark, solid crust beneath a sky filled with stars. Winds rush across the boundary between light and darkness, attempting to balance the extreme temperature difference. Heated air rises on the day side and flows toward the night, creating powerful global currents. The entire planet exists in a delicate equilibrium between blazing radiation and gravitational restraint. These ultra-fast worlds are often slightly larger than Earth, composed mostly of rock and metal. Their proximity to their stars stretches them subtly, creating tidal bulges that pull at their interiors. Over time, that constant stress may trigger volcanic activity or reshape their crust. Some may even be slowly spiraling inward, inching closer to their stars with each passing orbit. Astronomers detect these planets both through transits and stellar wobbles. Because their orbits are so short, their signals repeat quickly, making them easier to confirm. Every few hours, the star dims slightly as the planet crosses in front. The rhythm is steady, precise, almost like a heartbeat. If you could watch one of these systems from afar, the motion would feel urgent. The planet would sweep around its star again and again, a rapid arc traced in light. And yet, despite their speed, these worlds may endure for billions of years, locked in gravitational embrace. As we drift away from these racing sparks, the contrast becomes clear. Some planets hurry through their existence, while others move with extraordinary patience. Ahead, we approach worlds whose journeys around their stars unfold so slowly that a single orbit may span entire millennia. As we leave behind the racing worlds that circle their stars in mere hours, the tempo of the cosmos softens once again. Motion slows. Orbits stretch outward into vast ellipses. Here, planets move with extraordinary patience, completing a single revolution not in days or years, but in centuries, sometimes even 1,000 Earth years for one full orbit. Imagine a gas giant drifting at the far edge of its star's gravitational reach. The star itself would appear small and distant in the sky, casting a pale and steady glow. Its warmth would be faint, barely enough to stir gentle atmospheric currents. If the planet possessed moons, those moons might orbit in quiet procession, illuminated by a sun that feels more like a bright star than a blazing disk. On such distant worlds, seasons would unfold slowly beyond human comprehension. If the planet's orbit is elongated, it might spend centuries creeping closer to its star, warming gradually, before retreating again into cold darkness for another long arc. Generations could pass during a single seasonal transition. Climate shifts would not feel like annual events, but like epochs. These long-period planets are difficult to discover. We cannot wait hundreds of years to observe a complete orbit. Instead, astronomers capture only a brief segment of motion, a subtle curve traced across the sky. From that partial arc, they calculate the full path using the steady mathematics of gravity. In some cases, powerful telescopes directly image these distant giants, separating their faint glow from the light of their parent stars. Temperatures on these worlds can be extremely low. Thick atmospheres may trap what little warmth is available, forming layered clouds that drift slowly across subdued skies. If water exists, it may freeze solid at the surface, while deeper layers remain liquid due to internal heat. Beneath a crust of ice, oceans might move quietly, insulated from the cold vacuum above. Standing on such a planet, if that were possible, you would witness a sky dominated by stillness. The star would rise and set over many months. Night would reveal a brilliant tapestry of distant suns untouched by glare. Comets and icy bodies might occasionally pass through the system, tracing luminous arcs that fade over decades. These distant travelers remind us that the universe does not rush. Gravity binds across enormous spaces, holding star and planet together even when separated by billions of miles. And as we continue drifting, another realization gently emerges, that beyond all these individual systems, there are not just dozens or hundreds of planets, but thousands upon thousands already discovered, each one quietly orbiting its star in the vast and patient dark. As we move beyond these distant, slow-turning giants, a larger picture begins to form. The individual worlds we have visited, the blazing, the frozen, the dark, the swift, are not rare exceptions scattered sparsely across space. They are part of something far greater. Over the past few decades, astronomers have confirmed not dozens, but thousands of planets beyond our solar system. For most of human history, we knew only one planetary family, our own. The sun at the center, with its familiar companions circling in steady order. The wandering lights in our night sky were once mysteries, then neighbors, then destinations for spacecraft. But beyond them,
For centuries, we could only imagine whether other stars held worlds of their own. That uncertainty changed in the 1990s when the first confirmed exoplanets were detected. At first, they were surprising, massive gas giants orbiting extremely close to their stars. These hot Jupiters challenged our expectations. Over time, as telescopes grew more sensitive, smaller and distant planets emerged from the data. Rocky worlds, super-Earths, mini-Neptunes, planets in tightly packed systems, and others drifting far from their suns. Space telescopes dedicated to planet hunting have transformed our understanding. By patiently watching thousands of stars for tiny dips in brightness, they revealed that planets are not rare accidents, they are common. Many stars in our galaxy likely host planetary systems. Some stars may have only one companion. Others may hold intricate arrangements of multiple worlds, each orbiting in delicate balance. Statistical studies now suggest that there could be hundreds of billions of planets in the Milky Way alone, perhaps more planets than stars. Worlds of every size and temperature, orbiting red dwarfs, yellow suns, blue giants, and faint remnants alike. Each new discovery reshapes our perspective. We once believed our solar system might be typical. Now we see that planetary systems vary widely. Some are compact and crowded, others are sparse and expansive. Some contain planets like nothing we have ever observed up close. And yet, despite the vast numbers, every planet remains a single place, a sky, a surface, an atmosphere shaped by gravity and time. Even though we may never visit most of them, we can measure their presence through light and motion. As we drift onward through this immense population of worlds, another subtle truth emerges. Many of these planets were not found by seeing them directly, but by studying the delicate fingerprints left in starlight, patterns so faint that they require extraordinary precision to uncover. And in those patterns, entire planetary systems quietly reveal themselves. As we continue drifting through this vast population of worlds, we begin to understand something remarkable. Most planets are not seen, they are inferred, discovered not by images, but by patterns written delicately into starlight. When astronomers study distant stars, they do not simply look at brightness. They split the light into spectra, rainbows of information stretching across wavelengths. Within those spectra are tiny absorption lines, dark marks where specific elements absorb light. When a planet orbits a star, its gravity causes the star to shift ever so slightly. That motion subtly stretches and compresses the starlight itself. As the star moves toward us, its spectral lines shift toward blue. As it moves away, they shift toward red. This oscillation repeats with steady rhythm, revealing the unseen planet's orbital period. The amplitude of that shift tells us about the planet's mass. Even if the world itself remains invisible, its presence is etched into the light. In some systems, multiple planets tug on their star at once. The result is a complex pattern of overlapping signals, gravitational harmonies layered atop one another. By carefully disentangling these signals, astronomers reconstruct entire planetary systems, mapping worlds that cannot be photographed directly. Beyond motion and shadow, there is yet another subtle clue: timing. In tightly packed systems, planets can gravitationally interact with one another, slightly altering their expected transit times. A transit may occur a few minutes early or late. That tiny variation signals the pull of a neighboring planet. Through these minute shifts, hidden companions reveal themselves. It is astonishing how much can be learned from such faint evidence, from changes smaller than a fraction of a percent in brightness, from velocity shifts measured in meters per second across light years of space, from timing variations lasting only moments. And within those measurements, we find worlds with thick atmospheres, others stripped bare, some with densities suggesting iron-rich cores, others so light they must be composed mostly of gas. We begin to estimate temperatures, atmospheric chemistry, even the potential presence of clouds. We are, in essence, listening to the music of starlight, detecting planets through the subtle notes they imprint upon it. As we drift onward, that music grows richer still. Some planets reveal atmospheres not only stable and layered, but dynamic, with clouds shifting across their skies, winds redistributing heat, and perhaps even signs of water vapor suspended in distant air. The quiet study of light begins to hint at weather unfolding on worlds far beyond our reach.
As we continue listening to the music of starlight, the details become softer, more intricate. Beyond mass and orbit, beyond size and distance, we begin to sense atmosphere, the thin veil of gas that wraps a planet and shapes its character. And remarkably, even across dozens or hundreds of light years, we can detect hints of those distant skies. When a planet passes in front of its star, a small portion of starlight filters through the outer layers of its atmosphere before reaching us. Different gases absorb different colors of light. Hydrogen leaves one signature, sodium another. Water vapor, methane, carbon dioxide, each marks the spectrum in its own subtle way. By measuring these faint imprints, astronomers can reconstruct the composition of alien air. Some exoplanets show clear signs of thick, hazy atmospheres. High-altitude clouds scatter light, muting certain wavelengths. Others reveal transparent skies, allowing deeper atmospheric layers to be studied. In a few remarkable cases, water vapor has been detected. Not oceans confirmed, but the building blocks present in vapor form, suspended in distant air. Clouds on these worlds are rarely like Earth's soft white formations. Many are composed of silicate particles or metallic compounds. On extremely hot planets, clouds may contain vaporized rock that condenses into fine droplets high above the surface. These clouds can drift across hemispheres, carried by supersonic winds that attempt to balance the contrast between day and night. On cooler planets, methane or ammonia clouds may form in layered bands, reminiscent of Jupiter, but under entirely different conditions. Some worlds appear permanently overcast, wrapped in thick blankets of haze that obscure whatever lies below. Others show variability, brightness that changes over time, suggesting dynamic weather patterns shifting across the globe. Through repeated observations, astronomers can even detect temperature differences between a planet's day side and night side. By measuring infrared light as the planet orbits, they map heat distribution, watching how efficiently atmospheres circulate warmth. Some worlds show extreme contrasts, blistering daylight and frigid darkness. Others demonstrate remarkable balance, with winds carrying heat evenly across their surface. All of this is learned from light, from photons that began their journey years ago and arrived carrying delicate information about faraway skies. As we drift deeper into this expanding gallery of possibilities, another thought gently emerges. Among these countless planets, some may orbit within regions where temperatures are neither too hot nor too cold.
places where liquid water could exist steadily on the surface. Worlds that sit in the quiet middle ground, balanced carefully within the habitable zone of their stars. As we drift gently onward, leaving behind the shifting clouds and mineral skies, we arrive at a quieter possibility. Planets that orbit at just the right distance from their stars. Not so close that their oceans would boil away, not so far that water would freeze into permanent ice. This region is often called the habitable zone, the narrow band where temperatures may allow liquid water to exist steadily on a planet's surface. But habitability is more than distance alone. A planet's size, atmosphere, and internal heat all play delicate roles. Some of the most intriguing candidates are known as super-Earths, rocky planets larger than Earth but smaller than Neptune. With stronger gravity, they may hold on to thicker atmospheres. That thicker air could regulate temperature more effectively, smoothing out extremes between day and night. Imagine standing on such a world. The sky might appear slightly denser, perhaps tinted by unfamiliar gases. Clouds could drift across continents under a sun that appears a little larger or smaller than ours. If oceans exist, they might stretch wider and deeper than Earth's, influenced by stronger tides. Mountain ranges could rise under increased gravity, their slopes shaped by subtle differences in erosion and pressure. Some super-Earths may experience fewer tectonic disruptions than our own planet, offering long periods of climatic stability. Others could have more active interiors, fueling volcanoes and recycling atmospheric gases through planetary processes. Stability and change, both are possible outcomes, depending on mass and composition. Astronomers identify these promising worlds through careful measurements of size and orbital distance. When combined with stellar data, they estimate surface temperatures. In a few cases, atmospheric hints suggest the presence of water vapor or carbon-based molecules. These clues do not confirm life, but they invite curiosity. Even small red dwarf stars, cooler and dimmer than our Sun, can host habitable zones, though much closer in. Planets there may be tidally locked, with one hemisphere facing the star constantly. Yet climate models suggest that with a thick enough atmosphere, heat could circulate efficiently, allowing temperate regions to exist along the boundary between light and dark. The idea that some of these distant worlds might hold conditions suitable for life is both humbling and calming. It reminds us that Earth may not be unique in its balance, only one example among many possibilities. And as we continue drifting outward, the scale widens again. Beyond individual habitable zones and planetary families, we begin to sense the grand architecture of the galaxy itself, a vast spiral of stars, each potentially accompanied by its own quiet collection of worlds. As we drift beyond individual stars and their carefully balanced habitable zones, the perspective widens. The planets we have visited are not isolated curiosities scattered randomly through space. They belong to something far larger, the slow spiraling structure of our galaxy. The Milky Way stretches across 100,000 light-years, a vast rotating disk of stars, gas, and dark matter. Within its spiral arms, new stars are born from collapsing clouds of dust.
Around many of those newborn stars, disks of material gather and flatten, forming the seeds of planetary systems. Over millions of years, particles collide and merge, building rocks, then worlds, then fully formed planets. If planets are common around stars, and evidence strongly suggests they are, then our galaxy may hold hundreds of billions of worlds. Some orbit close to bright, massive stars that burn fiercely and briefly. Others circle small red dwarfs that glow steadily for trillions of years. Some reside near the crowded galactic center, where stars are packed tightly together. Others drift quietly in the outer arms, where space feels more open and sparse. Even the movement of our own solar system through the galaxy has shaped its history, passing through spiral arms and regions of varying density over hundreds of millions of years. From our vantage point on Earth, the Milky Way appears as a soft band of light arcing across the night sky. Yet within that luminous ribbon are uncountable stars, each potentially surrounded by planets unseen. Every point of light may represent not only a star, but a system of worlds, some hot and violent, others calm and ocean-covered, some perhaps drifting alone. The galaxy itself rotates slowly, taking over 200 million years to complete one full turn. During that time, stars shift positions, clouds collapse, and new planets form while older ones fade or transform. The story of planets is woven into this larger motion, a tapestry of gravity and time. As we continue drifting outward in thought, beyond even the spiral arms, another realization emerges. Our galaxy is not alone. It is one among billions. And if planets are common here, they may be common everywhere, scattered across the universe like grains of sand, each orbiting quietly in its own corner of cosmic night.
As we gently leave the spiral arms of our galaxy behind, the scale expands once more. The Milky Way, vast as it is, becomes just one luminous island among billions. Beyond it lie other galaxies, some spiral like ours, some elliptical and smooth, others irregular and scattered. Each one holds billions or even trillions of stars. And if planets are common around stars here, they may be just as common there. Imagine drifting between galaxies, where space grows even darker and quieter. The nearest large neighbor, Andromeda, glows faintly in the distance, its light having traveled over 2 million years to reach us. Within it are countless stars, each potentially surrounded by its own collection of worlds. Planets orbiting stars we will never see individually, worlds that will remain forever beyond our reach. The laws of physics do not change from galaxy to galaxy. Gravity binds matter, gas collapses into stars, disks of dust swirl into planets. The same quiet processes that formed Earth may be unfolding across unimaginable distances. There may be ocean worlds circling suns in distant galaxies. There may be rogue planets drifting in intergalactic darkness, far from any star at all. And yet, even as the scale becomes overwhelming, the motion remains gentle. Galaxies rotate slowly, stars orbit their galactic centers, planets circle their stars. From the smallest orbit to the grandest spiral, everything moves in patient arcs. Light from distant galaxies arrives as faint smudges in our telescopes.
We cannot detect individual exoplanets so far away, not yet, but statistically they must be there. If each galaxy holds billions of stars and many stars hold planets, then the universe is filled with worlds beyond counting. Some may resemble the scorching giants we passed earlier. Others may be frozen spheres in distant orbits. There could be super-Earths bathed in gentle sunlight, or tidally locked planets where life, if it exists, thrives in twilight bands between day and night. The universe does not announce these worlds loudly. It does not reveal them all at once. Instead, it offers hints, patterns in light, subtle motions, faint signals gathered patiently over decades. And as we begin to drift inward again, from the scale of galaxies back toward individual stars, we are reminded of something quietly profound. Every planet, no matter how distant, is part of the same cosmic story, shaped by gravity, guided by time, and carried through the dark on a steady, unbroken path. As we drift back inward from the vastness of galaxies, the scale narrows once more, from clusters of billions of stars to single systems, from spirals of light to the quiet glow of one distant sun. And within these systems, something even more subtle unfolds. Time itself begins to shape the fate of planets. Stars are not constant. They are born, they shine, and eventually they change. A young star burns brighter and more erratic, flaring with bursts of radiation. Planets forming around it must endure that early turbulence. Their atmospheres may be stripped, reshaped, or chemically altered. Some worlds lose their lightest gases in these early years, becoming smaller and denser than they began. As stars mature, they often settle into long periods of stability. During this steady phase, planetary climates can stabilize as well. Oceans, if present, may persist for billions of years. Atmospheres circulate gently. Geological processes shape continents or crusts. The star provides consistent warmth, allowing conditions to unfold gradually. But eventually, change returns. Stars like our Sun will expand into red giants, swelling outward as their internal fuel shifts. Inner planets may be engulfed. Outer planets will feel rising temperatures as the star grows brighter and cooler in color. Ice worlds may briefly thaw. Frozen moons may experience fleeting warmth before the star sheds its outer layers. Even after this transformation, planetary systems do not simply vanish. Some worlds may survive the red giant phase, shifting into new orbits around a white dwarf remnant. Others may be cast outward, becoming rogue planets drifting alone. Debris from destroyed worlds may gather into new disks, seeding future planetary formation in rare cases. Time reshapes every system differently. Some planets spiral slowly inward over millions of years, drawn by tidal forces. Others migrate outward due to gravitational interactions with neighboring giants. Orbits stretch, tilt, and sometimes destabilize entirely. And yet, through all this change, gravity remains steady. Planets continue tracing arcs. Stars continue evolving. Motion never truly stops. If we could watch a single planetary system over billions of years, we would see not a static arrangement, but a living architecture of motion and transformation. Worlds forming, shifting, fading, and sometimes re-emerging in altered forms. As we continue drifting through this unfolding timeline, another quiet realization emerges. Among all these changing systems, the burning giants, the frozen wanderers, the mineral-clouded skies, there are still mysteries we have only begun to glimpse. signals that hint at something more complex than rock and gas alone. Subtle patterns in light that raise a gentle question about what else might be possible on distant worlds.
As we continue drifting through these evolving systems, the questions grow softer yet deeper. Beyond mass and orbit, beyond heat and chemistry, there is a quieter possibility, one that does not announce itself loudly but lingers at the edge of measurement. Could some distant planets hold not only oceans or atmospheres, but something more complex unfolding within them? Astronomers search for what are called biosignatures, chemical patterns in a planet's atmosphere that might suggest biological activity. On Earth, life has reshaped the air itself. Oxygen, for example, is abundant in our atmosphere largely because of photosynthetic organisms. Methane, too, can be produced by living processes. When found together in certain proportions, these gases can signal imbalance, a state difficult to maintain without continual replenishment. If we were observing Earth from dozens of light years away, our planet's spectrum would show oxygen, water vapor, carbon dioxide, and subtle traces of methane. Those fingerprints might hint to distant observers that chemistry here is not entirely passive. In the search for similar patterns elsewhere, telescopes analyze starlight filtered through exoplanet atmospheres. So far, no confirmed biosignatures have been found, but hints of water vapor, carbon-bearing molecules, and complex atmospheric dynamics continue to emerge. Each new observation refines our understanding of what is possible. Some planets orbit small red dwarf stars where habitable zones are close in. These stars can flare intensely in their youth, emitting bursts of radiation that may challenge the survival of early atmospheres. Yet models suggest thick atmospheres or magnetic fields could provide protection. In the twilight bands of tidally locked worlds, moderate conditions might persist for long stretches of time. Life, if it exists elsewhere, may not resemble anything we know. It might thrive beneath ice-covered oceans, shielded from radiation. It could exist in forms adapted to thick atmospheres or dim light. The universe does not limit itself to one design. And yet, even without confirmation, the search itself is calming. It reflects a patient curiosity, a willingness to listen carefully to faint signals across immense distances. The same light that reveals mineral clouds and atmospheric escape also carries the faintest chemical whispers. As we drift onward, we recognize that whether or not life is found beyond Earth, the diversity of planets alone is extraordinary. Each world is a complete system, shaped by gravity, chemistry, and time. And still, there remain phenomena even stranger. Planets that orbit backward against the spin of their stars, moving in quiet defiance of the disks from which they were born. As we continue our quiet journey, another subtle surprise emerges from the data. Some planets do not move in harmony with their stars. Most planetary systems form from a rotating disk of gas and dust. The star spins in one direction, and the planets that form from the same disk usually orbit in that same direction. It is a graceful alignment, a shared sense of motion carried from birth. But not always. Astronomers have discovered planets whose orbits tilt dramatically relative to their star's rotation. Some even move in the opposite direction entirely, orbiting backward. These retrograde worlds circle against the spin of their own suns, defying the expectation of orderly formation.
How could this happen? Over long stretches of time, gravitational interactions can reshape entire systems. A massive neighboring planet might shift or migrate inward, disturbing the orbits of smaller worlds. A passing star could tug subtly during a close encounter, tilting orbital planes. In multi-star systems, the complex pull of companion stars may gradually twist a planet's path until it flips. The result is a planet tracing a path that seems almost rebellious, not aligned with its star's rotation, but cutting across it at a steep angle or circling in reverse. From the surface of such a world, the sky might not reveal this unusual motion directly. The star would still rise and set, though the timing and orientation of seasons might feel unfamiliar. The true difference lies in the deeper mechanics, in the invisible geometry of orbit and spin. Many of these retrograde planets are hot Jupiters, massive worlds that likely migrated inward from more distant origins. Their current positions suggest turbulent histories, gravitational reshuffling that left them locked in tight, close-in orbits while tilted or reversed. These discoveries remind us that planetary systems are not frozen in their initial designs. They evolve, they interact, they sometimes become chaotic before settling into new forms of balance. Even in apparent disorder, gravity finds a way to sustain motion. A backward orbit does not mean instability, only a different history written into the architecture of the system. As we drift onward from these quietly defiant worlds, another gentle wonder appears ahead. Planets so reflective that they shine brightly against the darkness, their cloud tops scattering starlight in luminous brilliance, almost like mirrors suspended in space.
As we leave behind the backward moving worlds, something brighter begins to emerge ahead. Planets that do not swallow light, but reflect it generously. While some worlds are darker than charcoal, others gleam like polished mirrors, their thick cloud tops scattering starlight back into space. These highly reflective planets have what astronomers call a high albedo, a measure of how much light a surface reflects. On Earth, clouds contribute significantly to our planet's brightness from space. But on certain exoplanets, reflective clouds dominate almost entirely, creating worlds that shine intensely against the darkness. Imagine approaching a gas giant wrapped in thick, pale clouds. From a distance, it might appear creamy white or softly golden, glowing in the light of its nearby star. These clouds may be composed of silicates, ammonia, or other condensed materials, depending on temperature. In some cases, metallic compounds can form reflective layers high in the atmosphere, bouncing light outward like a shimmering shield. Such reflectivity can influence the planet's climate. By sending much of the incoming radiation back into space, these clouds may prevent extreme heating. Even planets relatively close to their stars can remain cooler than expected if their cloud cover is thick enough. The balance between absorption and reflection becomes a delicate atmospheric dance. On these bright worlds, the sky from the surface, if one could stand upon it, would be luminous and diffused. Light filtering through thick clouds would scatter evenly, softening shadows. Storm systems might swirl visibly in wide bands, their edges glowing under starlight. Lightning could flicker within cloud layers, illuminating vast atmospheric currents. Some of these reflective planets orbit stars cooler than our Sun, where cloud chemistry allows thicker condensates to form.
Others circle hotter stars but maintain brightness through unusual atmospheric compositions. Each one represents a different solution to the same fundamental equation: how a planet manages the energy it receives. Astronomers determine reflectivity by measuring how much light a planet contributes as it orbits its star. In certain cases, they observe a slight brightening when the planet moves to the far side of the star, reflecting light toward us. From these faint signals, they estimate cloud thickness and atmospheric composition. These shining worlds remind us that planets are not merely passive recipients of starlight. They respond, reflect, absorb, and redistribute energy in complex ways. And as we continue drifting, another possibility begins to unfold. Planets locked in deep gravitational embrace with their stars, where tidal forces reshape not only their orbits, but their very interiors, generating hidden heat beneath their surfaces.
As we drift closer to these tightly bound systems, gravity begins to feel less like a distant force and more like a shaping hand. Some planets orbit so near their stars that tidal forces stretch and compress them continuously. This steady gravitational pull does more than guide their motion, it reshapes their interiors. On Earth, tides gently raise and lower our oceans due to the moon's gravity. But on certain exoplanets, tidal forces are far more intense. A massive star pulling on a close-in rocky world can flex the planet's crust rhythmically, generating internal friction. That friction produces heat, sometimes enough to melt rock beneath the surface. Imagine a planet slightly larger than Earth orbiting extremely close to its star in an elongated path. Each time it swings closer, tidal forces strengthen, squeezing its interior like a slow cosmic heartbeat. Magma chambers may expand and contract. Volcanoes could erupt frequently, resurfacing the planet again and again. Entire landscapes might be shaped by relentless internal warmth rather than sunlight alone. Even moons around giant exoplanets may experience this effect. If a moon orbits a massive planet that itself lies close to a star, tidal heating could create subsurface oceans beneath icy crusts. Though starlight is distant or weak, internal energy may keep water liquid deep below the surface. This hidden heat is not always visible from afar. Astronomers detect it indirectly through slight temperature variations, unusual atmospheric signatures, or subtle orbital shifts. Some planets appear warmer than their distance from the star would suggest, hinting at internal energy sources beneath their crusts. Tidal locking often accompanies such close orbits. One side of the planet faces the star constantly, while the other remains in perpetual night. But beneath that surface contrast, the entire planet may be alive with slow internal motion. The day side bakes under starlight, the night side cools into shadow, and deep below, molten currents move silently. These worlds demonstrate that not all planetary heat comes from above. Some is generated from within, shaped by gravity's steady pressure over immense spans of time. As we drift away from these flexing, molten landscapes, the cosmos presents yet another variation. There are planets whose densities are so light that they seem almost impossibly light, puffed-up giants with atmospheres so extended that they resemble fragile spheres of mist barely held together by gravity's gentle grip.
As we move beyond those molten, tidally flexed worlds,
we encounter planets that seem almost impossibly delicate. These are the so-called puffy planets, gas giants so low in density that they would float, if such a thing were possible, in an ocean vast enough to hold them. Compared to Jupiter, they may be similar in size, yet only a fraction of the mass. Imagine a planet as large as Jupiter, but with the density of cotton candy. Its atmosphere stretches outward, extended and diffused, heated by the nearby star. The outer layers are gently inflated, creating a sphere that appears oversized for its mass. Gravity still holds it together, but only just, like a soft balloon drifting in space. Many of these inflated giants orbit close to their stars. Stellar radiation heats their upper atmospheres, causing them to expand dramatically. Some may also be young, still radiating leftover heat from their formation, contributing to their bloated appearance. Others may contain cores smaller than expected, composed mostly of hydrogen and helium with little heavy material at the center. From a distance, these planets look enormous when they pass in front of their stars, blocking more light than their mass would suggest. Their low density is revealed when astronomers combine transit data with measurements of stellar wobble. The size is large, but the gravitational tug is modest, a clue that the planet is mostly gas spread thinly across a vast volume. If one could descend into such an atmosphere, the transition would be gradual. There would be no solid surface to stand upon. Instead, the air would grow denser and warmer as depth increases, eventually merging into a thick interior of compressed gas. Storms might swirl lazily in wide bands, driven by heat differences between day and night. Some puffy planets lose material steadily, their outer layers drifting away under stellar radiation. Over time, they may shrink and cool, becoming more compact. Others may stabilize, maintaining their inflated forms for billions of years. These fragile giants remind us that planets are not always compact spheres of rock or tightly bound gas. Some are stretched thin by heat and youth, existing in a delicate balance between expansion and escape. And as we drift onward, leaving these airy worlds behind, we approach another quiet mystery: planets that orbit so far from their stars that they are barely illuminated at all, their faint light reflecting only the distant glow of a sun that appears as little more than a bright star in their sky.
As we move farther from the warmth of close-in stars, the light fades into something faint and silvery. Here we find planets orbiting at extraordinary distances, so far from their suns that daylight would feel more like a bright twilight. The parent star would appear not as a blazing disk, but as an intense point of light in an otherwise dark sky. These distant worlds trace enormous orbits that can take hundreds or even thousands of years to complete. Their gravitational bond to their star is gentle but persistent, holding them across billions of miles of space. Because they receive so little stellar energy, their surfaces, if they have surfaces, are often cold and quiet. Gas giants in these outer realms may resemble scaled-up versions of Jupiter or Saturn, but with slower atmospheric circulation. Without strong solar heating, their weather systems may be driven more by internal heat than by sunlight. Thick cloud layers composed of ammonia, methane, or other compounds could drift slowly across their upper atmospheres, illuminated faintly by distant starlight. If these planets host moons, those moons may become especially intriguing. Tidal heating from the giant planet's gravity could warm subsurface oceans beneath icy crusts, even in regions where sunlight is scarce. Beneath layers of ice, liquid water may persist for millions or billions of years, insulated from the cold vacuum above. On rocky planets in these outer orbits, temperatures could plunge dramatically. Surface water would freeze solid. Atmospheres might condense and snow down onto the ground as frost. Yet deep underground, radioactive decay could still provide modest warmth, sustaining pockets of liquid far below the surface. The sky on such a world would be breathtaking in its clarity. With the stars so distant and dim, the night would dominate. The Milky Way, or whatever galaxy surrounds it, would shine brightly overhead, uninterrupted by glare. Stars would appear sharp and numerous, creating a sense of quiet infinity. Astronomers detect these far-flung planets more often through direct imaging than through transits. Because they orbit at such wide separations, telescopes can sometimes distinguish their faint glow from the star's light. Infrared observations reveal the heat they emit, even when reflected light is minimal. These remote worlds remind us that not all planets live under bright suns. Some dwell in the outskirts, tracing slow arcs through cold expanses. And as we continue drifting through this widening tapestry of possibilities, another thought begins to form: that even our understanding of planets themselves may still be incomplete, shaped by what we can observe and limited by what remains hidden in the dark. As we drift deeper into this expanding tapestry of worlds, a quiet realization settles in. Everything we have described so far is shaped by what we are able to detect. Our telescopes capture shadows, subtle wobbles, faint glows in infrared light. But there may be entire categories of planets that remain hidden simply because our methods are not yet sensitive enough to reveal them. Most of the exoplanets discovered so far are either very large, very close to their stars, or positioned in ways that allow them to transit from our viewpoint. Smaller Earth-sized worlds in wide orbits are harder to find. Planets that never pass directly between us and their stars may remain invisible for decades. There could be countless quiet systems that have not yet whispered their presence to us. Even within known systems, mysteries linger. Some stars show faint, irregular dimming that does not fit simple planetary models. Others exhibit long-term brightness changes that hint at distant companions or dusty debris disks. In some cases, we detect planets whose densities challenge our expectations. Too light to be solid, too heavy to be pure gas, suggesting unfamiliar internal structures. Technology continues to advance. New space telescopes are being designed to directly image smaller, cooler planets. Future instruments may be able to block out starlight with extraordinary precision, allowing us to see faint Earth-sized worlds orbiting in their habitable zones. Spectroscopy will grow more refined, capable of detecting increasingly subtle atmospheric signatures. With each improvement, the gallery of known planets expands. Worlds that once seemed impossible become commonplace. Hot Jupiters were once a surprise. Super-Earths were once theoretical. Now they are frequent discoveries. And yet,
For all our growing knowledge, the universe retains its calm vastness. Most planets will remain distant points of data. We will know their mass, their radius, perhaps the composition of their air, but never feel their wind or stand beneath their skies. Still, there is something soothing in this gradual unfolding. Discovery does not rush. It arrives patiently, one signal at a time. Each faint dip in starlight adds to a larger mosaic. As we continue drifting toward the quiet close of this journey, one final truth becomes clear. The diversity of planets is not the exception, it is the rule. The cosmos does not repeat a single design. It experiments endlessly, shaping worlds of fire, ice, shadow, and light across unimaginable distances. As our journey begins to slow, we find ourselves floating between all the worlds we have visited. The blazing giants, the frozen wanderers, the reflective clouds, the backward orbits, the patient centuries-long revolutions. Each planet moves in its own quiet rhythm, yet all are bound by the same simple forces: gravity, motion, time. It is easy to think of planets as isolated spheres drifting alone in darkness, but every world is part of a larger relationship. A planet and its star are partners in orbit, circling a shared center of mass. Moons circle planets, rings form from shattered remnants. Even rogue planets, cast free from their systems, still carry the imprint of their origins, the elements forged in ancient stars, the heat retained from their formation. Across the galaxy, this dance repeats endlessly. Gas clouds collapse, stars ignite, disks flatten and spin, dust grains collide and merge. Over millions of years, worlds emerge from chaos into balance. Some endure for billions of years in steady orbit. Others migrate, collide, or dissolve under radiation. Nothing is entirely static. Everything moves. If we could step outside time and watch the Milky Way from afar, we would see countless tiny arcs, planets tracing invisible loops around their stars. From that perspective, no single world would stand out as special, and yet, from within each system, that planet would feel central, complete, the entire horizon of existence. Our own Earth is just one of these arcs, one orbit among billions. The same gravitational equations that guide distant super-Earths also guide us. The same starlight that reveals exoplanet atmospheres warms our oceans. The same cosmic processes that sculpt mineral clouds elsewhere shaped our skies long ago. There is comfort in that continuity. The universe does not divide into here and there as sharply as we sometimes imagine. The atoms in our bodies were forged in stars like those we observe across the galaxy. The iron in distant planetary cores share ancestry with the iron in our own. And so, as we gently approach the quiet end of this drifting exploration, the vastness no longer feels overwhelming. It feels interconnected. Every distant planet is part of the same unfolding story, a story written in gravity and light. And in that immense, steady motion, there is something deeply calming, a reminder that even across billions of miles, the universe moves in quiet, predictable rhythms, carrying every world, including ours, forward through the dark. And now, as our journey settles into stillness, we let the vastness grow quiet around us. We have drifted past scorching giants and frozen oceans, through twin sunsets and starless wanderers, across centuries-long orbits
and hours-long years. Each world different, each one real, each moving in patient obedience to gravity's steady pull. If you pause and imagine them all at once, the galaxy no longer feels empty. It feels alive with motion. Billions of stars, billions upon billions of planets, some wrapped in mineral clouds, some glowing faintly from internal heat, some racing close to their stars, others circling so far away that their sunlight is barely more than a distant spark. And yet, none of them hurry. Planets do not rush their orbits. Stars do not strain against gravity. Everything unfolds according to laws that are simple, elegant, and constant. A planet forms from dust. It settles into motion. It evolves under heat, radiation, and time. Perhaps it holds oceans. Perhaps it remains barren. Perhaps it drifts alone between the stars. Whatever its path, it continues, silently, steadily. The same is true here. Our Earth turns gently beneath us, completing one quiet rotation every 24 hours. It circles the sun once each year, just as it has for billions of years. We rarely feel that motion, yet it carries us through space at astonishing speed. Around us, the solar system moves within the Milky Way, and the Milky Way itself drifts through the larger universe. Everything is in motion, and yet everything feels calm. The planets we have imagined tonight are distant beyond measure, but they are not separate from us. They are shaped by the same gravity, formed from the same cosmic materials, guided by the same physics. The iron in their cores was forged in ancient stars, just like the iron in our blood. As the universe expands quietly outward, these worlds continue their arcs. Some will change, some will fade. New ones will form in swirling disks of dust around newborn stars. The story does not end, it simply continues, patiently, across scales too vast to fully grasp. And so we return gently to stillness. The stars remain above, steady and soft. Planets continue their silent revolutions. The cosmos does not shout its wonders. It reveals them slowly in whispers of light. And for tonight, that is enough.